Okay, so right, so let's get started for the day. So let's see here. So in terms of your remaining responsibilities, is there another nano quiz? I don't remember. It's whatever's on the course calendar. No more? Okay, then no more nano quizzes. Fabulous. I have one more written, but I suppose I'll save it for myself. Okay, so that means that your remaining responsibility is just your final project. So I'll take a quick look at your check-ins. You know, the not-so-secret reason for the check-in is mostly to make sure that you guys are being productive. If it turns out that you needed like a complete shift in your project topic that you realized at your check-in or whatever, that's actually fine. Like I'm just, its job in life is just to make sure that you have opened your project, done some amount of work, and realized that, like, I don't know, weird Monte Carlo rendering things are actually quite difficult to implement, even if they're easy conceptually, right? These are the sorts of things that you find when you start to actually code this stuff. So for your final project, remember that there are two components. There's a presentation and a write-up. I believe the write-up is due the day after the presentation. Before the end of this week, we will send out, and Helen, please don't let me forget, we will send out a schedule for you guys to sign up for a presentation time. Of course, it's great if you can support your your fellow students in the class by seeing the other presentations, but some of the times will have to be out of the hour-and-a-half window of this course, and of course we understand if you can't make it. Your presentation, please remember that live demos, as much as they're fun, unfortunately are discouraged. If we add 1 minute to each of our, 40-something presentations in this class, that's 40 minutes on the end of our class, and I have a flight to catch at the end of our presentation. So we're gonna try and keep you guys on schedule. Please practice your presentation. It's like, 2 or 3 minutes? So like practicing it, you could practice it like 10 times and still have the better part of an hour to do something else. Cool? Cool. Okay. I will have office hours this Wednesday. Next Wednesday, I will not, but hopefully you won't need them at that point. Yes?
For the presentation, is it, I couldn't necessarily just remember from like there.
Sure.
Is it kind of just like a demonstration of like, here's like the final product, what I did? Or is it more of like a step-by-step of like, here's what I did and here's like the process of how I got there?
A little bit of both, yeah. So for most of the projects in this course, it takes about 10 seconds to look at an image and know what you did. So telling us a little bit about the technical background and what you did to get there would be great. Yeah. Any other questions? In terms of common pitfalls, please stay within the page limit for the write-up. I know you all have many brilliant things to say, but of course, brevity of wit and is brevity something wit. Whatever, keep it short, I don't care. Just don't write so much, I don't want to read it. Sorry, your other professors might not say that, but they feel it. So keep it short and exciting and tell us all the cool stuff that you did. And again, the top project as discerned in a completely holistic and unfair fashion by your TAs and myself who gets a trip to SIGGRAPH, which is the big computer graphics conference. Sadly for you, this year it's in DC, so it's not as interesting as a place as it sometimes is, but you can hang out with my parents, because that's what they are. Cool. Any other questions about the sort of end game in this class? I think it's pretty straightforward. Cool. My one remaining announcement, in our next lecture on Thursday, it's less of a lecture and more, what I've done is invited graduate students from the different graphics groups here at MIT to present their research. Since you guys don't have a nano quiz anyway, I don't see any reason to have more lecture content. It's kind of cool. We've already assembled, I think, students from at least 5 or 6 different groups here in CSAIL. That'll tell you all kinds of computer vision, graphics research. Oftentimes they're looking for Europs to help them out. Of course, I encourage you guys to come join us, both to give these people the courtesy of having an audience, and also because there's some really cool stuff. You guys now have learned the full graphics stack all the way from, I don't know, geometry to rendering to displays. And you can see that actually here at MIT, there's people working on just about every one of those pieces in the different groups here. So that class will probably be on the short side, so come on time and we'll have the kind of every 10-minute grab bag of grad students. And you guys are welcome to keep these guys on schedule when it comes to talking, because if you think you guys are bad about going over your allotted times, you should work with PhD students. Okay, so today for our final piece of 6837's kind of technical content before we hit the end game for this course. Remember that this class, the organization is pretty straightforward, right? We started with sort of stuff in the ether, talking about spline curves, how to specify a scene, and so on. And we're kind of following the graphics pipeline all the way from concept to delivery. And of course, the very last piece of that, after you set up your scene, you've rendered it, you've written all of your algorithms for processing things, you've done all of your color computation, you push it through your GPU. Finally, it comes out of the GPU in the form of electrons moving through some big metal piece of God knows what, and it has to come out of your screen. And it's that very last piece that we're going to talk about today, and then we've kind of closed the loop of the graphics pipeline from beginning to end. And so that's our job today, is to talk just a little bit about different output devices and how they actually work, again, at a very abstract, kind of high level, just so you have some idea of like what your actual clientele is when you write graphics code. Yeah, so that's our basic plan. We'll talk a little about 2D displays, 3D displays, and then VR. I was just looking at my VR material today, and it's a little bit out of date because this stuff changes really, really fast. So we'll talk a bit about some of the considerations that go into this technology. By the way, it didn't used to change really fast at all. There's like 15 years where nothing happened, and then suddenly VR is interesting again. And just to highlight the kind of things that come up in this universe. All right, so to start out, of course, we've now covered basically the full graphics stack, right? So we spent most of 6837 is somewhere up in this upper part, right, where we talked about different graphics libraries, rendering techniques, whether it's, in this class, OpenGL, DirectX is the sort of competitor to that, and a little bit of that typically would happen on the application layer, like physics and so on. The last couple lectures, we started to move a little lower in the stack, in this sort of middle bottom layer, right? So here's where like maybe GLSL would live. Down here is where the actual graphics card is doing its work. And then finally, of course, that has to go out to your display. We've made our way all the way to the bottom. The kind of, in our race to the bottom here in 6837, of course, the kind of amazing thing is that this abstraction works, right? And you guys are all going to graduate and go get cool jobs in different industries, and you'll be working in different parts of the stack here. Or, I don't know, making money in finance, but I'm less interested in that. And when you do, the cool thing is you'll be like cycling away working on like your GLSL code, not worrying about the fact that like there's a whole video game running on top of it. Or maybe the other way around, you're working on, you're coding in Unity or whatever, and like sitting underneath Unity is like what, OpenGL shaders, physics, meshes, so on. They're talking to your GPU is talking to your display, and each of these can be swapped out in a pretty seamless fashion. This was not the case 15, 20 years ago. And graphics programming was just awful back then, right? So if you look, and still to some extent today, when you look at like video game code, especially, there's like, if your card is an NVIDIA GTX, then do this. If your card is this, then do that. If your card is that, do that. If you're the poor guy running the integrated Intel graphics thing, then just turn it off altogether. The good news is that although the capabilities of the different hardware is different, the way that we interface with them is very much the same. And because of that, essentially these days you can go out and buy whatever your favorite graphics card is, push it into your computer, buy your favorite monitor from a different company, and they all work together in this kind of happy family. Which is just amazing when you step back and think about it. So when it comes to display technologies, of course, there are many different options. The old school display, which I don't think we see all that often anymore, is a CRT. These days, of course, your laptop screen and your LCD on your desk is liquid crystal. And then there's many other ones, right? LED, plasma, organic, like OLED. My favorite is what goes on inside of projectors like what's here, which to me is like this crazy Rube Goldberg machine, and it's just amazing that these things work. And in each case, what goes into them is just this cable right here, right? It's just the same digital signal, like HDMI or whatever. Right, so the earliest displays, and back when I was in your position learning computer graphics, the display that I had was a CRT, cathode ray tube. And this is sort of the simplest one to understand, where essentially what you have is an electron gun, which is as terrifying as it sounds, sitting in the back of your monitor, right? These are monitors that like took up space. Remember those days? Yeah. And essentially what would happen, the reason is all the way in the back of the screen was this thing that would create electron beams those would go through this big open space, and they'd hit a screen in the front, which was covered with fluorescent or phosphorescent style material, where when you hit it with an electron, it produces some light, right? So this is converting electron motion into light energy. And so finally, we've talked quite a bit about rasterization. You can see where that term comes from. This actual grid of phosphorescent doodads on the front of your screen is called the raster, right? And so when you rasterize an image, or rasterize like a line or whatever on your computer, really the reason that that term evolved is because this was taking some piece of geometry and actually figuring out where that electron beam needed to go to draw it on the screen. So it was a pretty concrete problem. In fact, that technology and those algorithms predated the computer technology we use now to implement these things, right? Like they were implemented in hardware by an actual physical device that was like moving around the electron beam. So the basic physical process that's going on here is phosphorescence. And this is this idea that energy is absorbed by some substance and then it's released slowly as light. And why does that word slowly need to be there? Yeah.
I mean, it's not instantaneous that your screen stays up, but it's like slowly, like 16 milliseconds.
Yeah, which is slow for light, right? So that's absolutely right. So you have just one beam of electrons coming out of this cathode ray tube, right? What does that mean? Like how many pixels can I turn on at once, at least in the simplest version of this? One, right? And so what's really going on inside of this tube is we've got this thing zigzagging back and forth, lighting up these pixels one after the next. And then what happens is it just moves on. And the pixel is lit, and then it just stays lit. And roughly the amount of time that it stays lit is roughly the same as the amount of time it takes for that ray to return back to the same pixel again. Does that make sense? And so this is, remember old monitors, you had to worry quite a bit about the refresh rate, and that's roughly what was going on there. Yeah?
Was it, you said it's like roughly the same in terms of like how long it takes for it to lose all the light and how long it takes for the other thing to come back. Was it like designed that way, or
Yes.
was that like a happy coincidence?
No, it's absolutely designed that way. Yeah, you choose materials and you choose your light motion in such a way that those two things go together very well. And moreover, you need to choose them in such a fashion that is aware of the refresh rate of your eyeball. Because if this whole technology is too slow, it's not going to be very useful. Yeah. Yes?
Is that why they started off with really low resolution displays? Because they were trying to...
That's a good hypothesis. I have no idea. Yeah. Yeah, that's absolutely right. A lot of these things, I mean, probably, like there are a lot of, especially in the older display technologies, there was actually moving parts. And that really limited the refresh rate and the resolution. Absolutely. Of course, you can do really cool things with these sorts of old school displays. If you ever find one, I encourage you to play with it in a controlled and scientific fashion, of course. So here's an example, actually, from our own physics department here. So here's an old CRT TV, right? Old school box. I'm not sure why they put a box around the clock. I'm not sure what difference that makes on the wall. That's just to convince you that they're not messing with the clock when they do this. So they take a big magnet, they move in front of the CRT, and what happens to the display? It actually warps. Now, given how we now know how these displays work, remember they shoot electrons from the back of the screen, they hit the front, and whatever they hit is what lights up. What do you think is going on in this video? Yeah?
It's like influencing the electron's paths to hit like different areas, so it looks like you see things in the wrong place.
That's absolutely right. So this giant, and to be fair, I'm sure that's a very strong magnet. This giant magnet is essentially attracting or pushing away or whatever the electrons, and that warps the image because maybe they're pulled toward or pushed away from the magnet. And the display has nothing to do with that piece of glass or that pile of phosphorus right behind it, right? What's determining what you're seeing on the screen is these electrons that are getting shot at that piece of glass. And so when you affect their path, they land in the wrong pixel, and that's the image that you see. I do not encourage you to do this experiment with your laptop because you will not see the same effect. Okay. Right. It always looks like fun. I always kind of wanted one in my office to do that, but it's like the kind of thing you do once and then the novelty wears off. Of course, the big problem with those kinds of displays, well, like you have this ray gun, which is sitting in the back of this thing. And of course, you need some space between the thing that's shooting out the electrons and the actual display, right? Because that's the path that they take to the pixels. And that's what made these monitors so bulky. And so these days, our technology is closer to LCD, liquid crystal display. These are really great unless you have polarizing sunglasses on, in which case they can be a little problematic. So in your LCD display, they make use of a completely different physical phenomenon, right? So now they're not electrons flying around, but rather these monitors are lit just with a single light, or maybe a pattern of lights that's sitting in the bezel of your screen. That's why if you have a really crappy laptop like my own, sometimes the corner of the screen is a little brighter than the interior, which means it's probably time to buy a new machine. But in any event, that light is just a light bulb. It's not moving around. There's no, pile of electrons getting shot every which way. But instead, what happens is that you put the light through your screen in a polarized filter, which is sitting in the back. And then you have another polarized filter that's known as a twisted pneumatic. Many of you guys who are into physics probably know more about this than I do. And essentially what goes on is when you have a polarizing filter, you're restricting the light wave to go in a particular orientation, right? It's like in a particular plane. And so what happens in the LCD display is that this particular pneumatic material has this property that when you put electricity in it, the direction that the polarization that it prefers changes. It can rotate, say, 90 degrees, right? And so you have light that's going through your first polarized filter. Maybe it's going vertically like that. And then you have a second polarized filter, which can go in one of two directions, vertically or horizontally, depending on whether you apply electricity or not. So what goes on in an LCD display is that you can choose whether you want to twist this material or not, right? And when it's twisted from the polarization in the back, what happens? Yeah, you block the light, right? Because it's all polarized this way. Now you added a filter in front of it that only accepts light going the other way. And now when you want to display a pixel, you just flip it the other way, they agree, and it goes through. It's like a keyhole or something. And so the nice kind of beautiful thing about this particular technology is that it doesn't really depend on having this giant space between the source of your light and the display in front of it, right? So here's the sort of difference between these two cases. Yeah, and so anyway, of course, there are many details. The actual material here is a lot fancier than just two different layers that you somehow control from the outside. There's kind of a nice online explanation of what's going on.
If you were to zoom into the monitor you were using to watch this video, you would see
Right,
thousands
let me
of
see if I can turn up the volume a little. We're going to rely on internet videos a bit today because they have these nice zooms of what's going on that would be hard for me to draw.
You split up each pixel, you'll see a backlight, 3 color filters, and polarizers. As light leaves the backlight, it travels along different planes, including the horizontal and vertical planes. The first polarizer only allows light traveling along the horizontal plane to pass through it and onto the color filters, with another polarizer that only allows light to pass along the vertical axis. All the horizontal light waves are blocked, so no light reaches the color filters. This is where the liquid crystals come into play. If you were to look closely at one of these liquid crystals, you would see a transparent electrode on the front and the back, as well as etched glass on the front and the back. Liquid crystals typically orient themselves in random directions until the horizontally etched glass in the rear and the vertically etched glass in the front force them to twist into a predictable pattern. As light passes through the compressed liquid crystal, it naturally follows the path of the molecules, so that any light traveling along the horizontal plane exits along the vertical plane.
So this is a
By
detail here.
reintroducing the electrodes and passing electricity through them, we can get the molecules to align themselves in the direction of the electric flow, causing light to no longer twist when passing through the liquid crystal. When we place these crystals back into the pixel, we can see that the light from the backlight will pass through the horizontal filter, get twisted into a vertical position by the liquid crystals, and then flow through the vertical polarizer to the color filters. However, if we turn on the electrodes, then the light is no longer twisted by the liquid crystals and stops at the vertical polarizer.
All right.
By adjusting the amount of electricity that flows through each set of electrodes, we can control how much light reaches each color filter. And there.
All right, and then every single one of these videos after this explains that you need red, green, and blue for some reason. Anyway, right, so I think you guys get the main point here is that you have two different filters that are 90 degrees off from one another, and I guess in the twisted pneumatic one, you actually twist the light to align with the second filter. And if you turn this thing off, then the light just stays in its original orientation and then gets blocked by the outer filter here. It is just ridiculously cool that this is happening inside of your screen at like 30 frames a second. But that's, I digress. Of course, there are many different variations on the theme. The clock that, well, at least the clock that I have on my nightstand, I don't know if people still have these kinds of things, would be a reflective LCD, meaning that the light source is outside of your display. Right, so in this case, the light goes in, and the same technology is used to polarize it on its way out. Of course, you have transmissive one where there's actually a light source behind the screen that's coming out, like your laptop screen. So if you want color in a display like this, it's pretty straightforward. Essentially, all you do is you put a big pattern of red, green, blue, red, green, blue, red, green, blue in front of this black and white screen, and suddenly you have color, yeah? And of course, your pixels are so small that your eye doesn't see that pattern unless you get really, really right on top of it. And so that's what's allowing your display to have this sort of thing. So it's not that you're like somehow changing the wavelength that's coming out of your screen, you're just controlling these three components of light independently. And of course, as we already talked about a little bit, one key thing to notice here is that, of course, the red, green, and blue on this computer screen are shifted by 1/3 of a pixel each. Right? And so what does that mean? That means that when you look at an image, if you render it not quite the right way, what you'll see is like a really strange color shifted effect. This is less prominent on modern displays because they just have a lot of pixels in them. But certainly in the old school CRTs, this is a big issue. And so like we talked about before, this allows you to do some really interesting effects by being aware of the grid of the pixels on your screen. So for instance, if you wanted to render fonts, right? So fonts are kind of annoying to draw on your computer screen because text tends to be pretty small. And so anti-aliasing is really critical in that regime. And one thing you can do is rather than, like typically when you look at images stored on the computer, the abstraction is that red, green, and blue are what we might say is co-located, right? They're all at the same point. The reality is they're not. They're shifted from each other. And so in clear type font, what you would do is actually have 3 separate fonts for red, green, and blue that are slightly offset from one another so that you get that last little bit of anti-aliasing effect that takes advantage of the grid of pixels on your screen. What's going to be the problem with this? Yeah?
You might have weird color effects.
You might have weird color effects, that's absolutely right. So if you grab an old Windows 3.1 computer screen when they just started using these sorts of things, you could actually see a little bit of feathering on the side because the resolution was so low that you really could see the individual pixels. Any other challenges? Yeah?
Also computationally heavier.
It's computationally heavier. Maybe, I don't know. I mean, in both cases you have to draw the same number of pixels. But a different challenge can emerge, which is that if we decide that we want to make screens in a different way, then we need a new font, right? So in particular, remember that we talked about how your eye is less sensitive to blue than it is to red and green. So it might make sense to make a display where you have more red and green pixels than you have blue. In fact, those exist. But if you do that, well, you no longer have this RGB pattern, then you need a new clear type font that knows that you have a different filter in front of your screen, or else you'll get total garbage, and that will drive your eye crazy, right? Because now the anti-aliasing is happening on all kinds of weird shifted positions here. Okay, so those are our main kind of 2 old school display technologies, and of course there are many, many more out there. Probably the more brain dead display technology, this is the one that your theorist instructor can understand, is the LED display, like what they have on football fields. So there you have a giant display, and of course the viewer is very, very far away from the screen. So what you can do is, rather than having anything clever, you can just literally put a big array of red, green, and blue light bulbs and turn them on and off. This makes a lot of sense to me. And of course there are many variations on that theme. So in some sense, a plasma display is like a little tiny version of that, right? So in a plasma TV or a plasma computer, I don't know if there are that many computer screens out there. What happens is you have little cells now that are filled with some gas, neon, xenon, whatever. And these are like little lamps when you apply voltage, right? So think about the difference between all these different technologies we've seen so far. So in the CRT, the light energy is coming from this ray tube, which is in the back of the screen. In the LCD, the light energy is coming from just like a light bulb sitting on the outer panel, and then you're blocking the light. And a plasma display, you're actually producing light, but in this case, you're doing it by like exciting a gas, right? So you apply some voltage, and the gas gets excited, and it starts emitting electrons, and that's what creates your plasma display. Once again, to get red, green, and blue, nothing too exciting is happening. You just have a big pattern of red, green, and blue things. So here's a little video with a nice visualization of what this looks like. With another corny narrator. I love these guys.
The answer is the plasma.
Okay.
Each subpixel is filled with a mixture of gas, xenon and neon. When an electrical impulse of about 300
I love this
volts
stuff.
rushes through a subpixel on its way to the electrodes, electrons from the gas mixture are violently torn off and suddenly float freely. That drastically changes the state of the mixture. It's no longer gas. It's now plasma. It's a highly energized state of matter, but it's a state that lasts only as long as the electrical discharge. As soon as the discharge ends, the freed electrons immediately return to their places, and the plasma once again becomes gas. What's important is that as they return to their places, the electrons release their surplus energy in the form of ultraviolet rays. It's these rays that excite the subpixel, which gives off light that combines with the light given off by the two other subpixels, and together, they light up the pixel.
Okay.
Every second, the plasma screen sends more than 2 billion electrical impulses into the subpixels in order to turn the gas there into plasma.
And then once again, the video goes through and explains that you need red, green, and blue. But in any event, hopefully you can see this is sort of just a variation on the LED display. It's just producing light at every point rather than like taking light that's from some other source and then filtering it to turn it on and off. So another sort of variation on that particular technology is OLED style, which basically just uses a different kind of material to also produce light, in this case some organic stuff. So these are displays that don't need backlights, which is pretty cool. They tend to be pretty expensive and low lifespan, but of course that's changing by the day, and OLEDs are far more popular than they were a couple years back. Okay, so now for something completely different. There's one more display, which is sitting in, I think almost all the displays with the exception of CRT I can see somewhere in this room. The one additional one we can see in this room we haven't talked about is projector technology like DLP. And these are just incredible to me. I wish I were like the kind of engineer that worked on this stuff, because I just find it so cool. So in your DLP projector, like what we've got right here, what's going on is basically a giant array of little mirrors. And it's like this total ballet that happens inside of these devices. It's just incredible. So the way to understand what goes on inside of your projector, and this is why like constantly you have to go, so first of all, what are the engineering demands when you have a piece of technology like this? Well, you need really bright light. Yeah, that's the main thing, because you've got like your projectors all the way back here, your displays all the way out here. So you need a lot of energy going into this thing. So things like these LED style displays or something where you're just producing light on the side of your display is probably not such a great option, right? And so instead, what projectors try to do is just take a giant light bulb and then channel that light energy into a coherent image like what you see in front of you here. And the way that they do that, in some sense, is like the most brain-dead fashion possible. And what's so amazing is that this is possible, that they can do this. So what goes on inside of your projector, so here's your projector screen on the top. You have a big light source. These are expensive and annoying, and you have to purchase them all the time for my classrooms. But this is just a fixed light bulb. There's nothing exciting going on. There's no polarization, nothing. And now you have this chip, which is sitting in front of your light source, and literally this chip is composed of a giant array of little mirrors. Right? So the way to think about what's going on inside of your projector is kind of like, you're standing here with a mirror, and like, someone over there, Rachel's holding a light bulb and facing it at me, and like, what can I do? Well, if I want to light up Colton, I like face my mirror in his direction, and suddenly he has a spotlight, and then if I don't, I just like face it away, and literally there's just like some black thing on the other side of your projector. They call it a light absorber. I think it's just like a piece of black material, like plastic or something. I guess what you don't want is for this thing to melt, because there's a lot of heat going on in here. And so essentially what happens is when you turn on a pixel, this mirror just points its way out of the lens of your projector screen. When you want to turn off a pixel, it points toward this thing that just sucks up this light energy. So there's a lot of waste going on inside of this object. And the incredible thing is that this is happening in every pixel of this display, right? So there's just a giant array of these little pivoting mirrors that are moving at this ridiculously fast rate to produce the image that you see on the screen here. I think this is so cool. So in any event, what are the advantages and disadvantages here? Well, the question you should ask is like, okay, you've told me how to turn on and off a pixel. How do I like turn on a pixel halfway? Well, that's kind of tricky, right? Like I just have a giant light bulb. I can either point it toward the screen or point it off. Well, what happens is that this ballet happens so quickly that I can modulate vibrating back and forth between turning on and off that pixel in such a fashion to achieve different grayscale colors. And in case that wasn't a coordinated enough thing, you could also ask, well, then what if I want a color image? What do I do? Well, maybe I put a spinning wheel in front of my light bulb with red, green, blue, red, green, blue, red, green, blue, rotating around. And I coordinate the spinning of this object with the motion of these mirrors to create this composed image. And the fact that this can happen inside of your rear projection TV, inside of your DLP projector, to me is just like the most amazing mechanical Rube Goldberg machine happening on this micro scale that is just unfathomable to me that people have engineered. And trust me, when you open these things up, you can't see it, right? Like it doesn't look nearly as exciting as you hope, like some little guy pivoting around a mirror or something. But anyway, yeah, so that's what's going inside of your projector. And of course, the advantage is that they're very bright. You can get some very good resolution this way. The disadvantage is that they're really complicated and lots of things can break. And they do waste quite a bit of energy because a lot of it is just absorbed by that black thing on the other side. Does that make sense? This is just a crazy piece of technology. I think it's so cool. And we all take it for granted. I mean, it's just sitting right here in front of us. Of course, there are other kind of alternative displays that you've probably encountered somewhere in your life. One of them is sort of electronic paper. So think like your Amazon Kindle or whatever. The displays of the demands of a display like e-ink is pretty much exactly opposite of the demands of your projector, right? You don't really care about high brightness. In fact, that's kind of annoying when you're reading a book. And chances are the refresh rate can be really low, right? Because you're just going to put a page of text on the screen, and at least if you read like I do, that page of text is going to stay there for a long time, which is why your project write-ups don't need to be that long. Okay, but in any event, sort of the question here is, I've got the world's most boring display now, right? Like the refresh rate is low. I don't really care about contrast all that much. I don't even need a light source necessarily. Can I come up with a totally passive technology that just allows me to turn on and off pixels and then leave them there until you're done reading that page, right? And that's what goes on inside of e-ink. And so the amazing thing, which I didn't actually realize when the Kindle came out, the e-ink really is kind of some fashion of ink. There's some kind of a black dye. Kind of like, you remember these old toys where there's like a magnet and you wanted to like put a mustache on the guy, so you would pull the magnet out and it would pull the shavings to the top and you would see. That's like roughly what's going on inside of electronic paper. You apply charge, and then what happens is that it kind of flips. There's like white particles and dark particles. And depending on what charge you apply at a given point, either the dark ones or the light ones appear on top, right? And so you apply that rearranges at every pixel on your display which one you see, and then you don't need to use any more energy for your display. It just stays like that until you do something else. So this is different from all our other displays because this is like rearranging stuff rather than actively displaying an image on every single cycle here, which is good because it meets the demands of these sort of e-ink style book Kindle displays. Watching a movie on one of these devices would be extremely painful because if you've ever played with one of these e-ink books, you can see the refresh rate. Like when you click the next page, like it takes quite a while to rearrange. Yeah?
Oh, no.
No, just doing your thing. Okay. Of course, extending these displays in almost any fashion is quite difficult. So for example, if I wanted a color ebook, I think these exist, but they're not very common. You can get it, and essentially what ends up happening is, just like all these other technologies, you just have a big array of red, green, blue, but the issue here is that these devices aren't producing light, right? They're just reflecting light. It's like a page of a book. And the contrast is very low, and moreover, you just divided your resolution by 3, or I guess by 9 on a page, because now you have this big pattern of pixels. And my understanding is that like there's an actual chemical that's moving around when you apply charge to these things, and that takes up some space. So these are not super high resolution devices. They go, so when you start adding color, the resolution gets even lower. Cool, so those are sort of the primary 2D displays. Of course, there are many out there, and every year there are new ones. The fun technology to play with now are 3D displays. So you can do important things like render a cow with little tags in his ear. Of course, 3D display technology is simultaneously really cool and extremely difficult to engineer well for any number of reasons. Of course, everybody wants 3D displays, and that's been the case since this technology first arose, right? Because, well, we have 2 eyes, and that's for a reason. And of course, binocular vision is one of the main reasons that we can perceive depth. This isn't 100% true. You guys perceive depth all the time from a single image, right? You're playing a video game on your flat computer screen. You're perfectly happy to get a lot of depth information out of that. So this is just gravy, right? It's not like it's not completely necessary to make. There's a difference between a 3D display and displaying 3D content, and both of those are important things. We focused on the latter in this class. If you want to do stereo on a flat display, of course, there are many, many problems, and a lot of cool technologies out there. So they tend to cluster into 2 different types. So there's active and passive 3D displays. If you go to the movie theater, you can experience both. So in an active 3D display, this is something that requires, again, this kind of complicated ballet where maybe you're flipping back and forth between your left and your right eye, and you're coordinating that with like a pair of glasses on your face that's determining which image you're seeing. Whereas a passive display would be something like, I'm going to just send 2 different signals in 2 slightly different directions so that your eye sees them both at the same time. Right, so remember those old bookmarks from the 1980s with the little lenticular displays when you rotated them? It's like the world's simplest passive 3D display. But we'll go into some more detail. Of course, when we talk about 3D display, and the whole reason that we're doing this is for depth perception, and there are many different cues that you have to get right in a display like this. So in the kind of stereoscopic world, there's of course binocular disparity. This is your eyes rotate to focus on different things, right? If my hand is right in front of me, then they're pointed like that. When I'm looking somewhere in the back of the room, they point farther apart. And this is one of the kind of cues that you use to see depth. And there are other ones. Accommodation, invergence is another one. Has to do with how you focus. And of course, there are plenty of pictorial cues as well, right? So occlusion, right? So probably the circle on the right is closer to you than the one on the left. And size, right? So, as things get smaller, maybe they look farther away. Or even if they're the same size, if I put shadows, this is yet another way to perceive this stuff. Now, we've talked about this quite a bit in this course. When it comes to displays, the annoyance is that it's very hard to achieve all of these at the same time. Right? And so typically what a 3D display does is it kind of chooses the effects that they're going to try and replicate in your 3D display. And then maybe some of the other ones that get kind of off. And the question is your brain willing to cope with that or not? Right? And so a lot of like perceptual studies and experimentation is needed to get these kinds of things right. And moreover, different issues like latency and refresh rate become really critical in these displays, which are coupled to the motion of your head sometimes relative to something that's just fixed on like the wall. Okay, so for example, a good example where this can go wrong is if I have a flat 3D display. Of course, that's the 3D world that I really want to see, but of course that's not what happens because your display ends. So the reality is that like your monitor bezel gets in the way. And just that can be enough to break this illusion of 3D that you're trying to produce in the viewer of your computer screen. And in case that wasn't hard enough, unfortunately, as humans, we've evolved that like there are certain social cues and things that are really critical and actually are incorporated into your visual system, right? Like in your everyday life, at least in my everyday life, there's not people in your face just like this. And so that can be painful and uncomfortable to produce a 3D effect that would simulate divergence and disparity of having an object right in front of your eyes, or sort of forcing you to have a cross-eyed perspective relative to the amount that you might do that just in your normal viewing experience. And so there's a lot of perceptual studies out there that try to measure things like your comfort zone when you view things. And that's really critical. So for instance, in 3D movies, oftentimes when you film it, you know, the actor might be right in front of the camera, right? So if the camera had a particular 3D perspective, it might require your eyes to be pretty focused up close. But of course, when you watch a 3D movie, the viewing experience is quite different, right? Like the screen is far, far away from you. And so when you try to replicate that effect at that distance, it can require the viewer to like be completely cross-eyed to view the scene properly, which of course would be extremely uncomfortable and creates a lot of like literally headaches for people viewing these films. So there's actually some really clever algorithms out there where what they'll do is they'll say, okay, we know the comfort zone of your eye. We also know that viewing a 3D movie isn't really the same as interacting with a 3D object because the screen's so far away, the display is what it is. So maybe what we'll do is like mess with the depth in a way that you're perceptually unlikely to notice, but makes your eyes more comfortable because you're more like watching a movie screen far, far away than like having a character right up in your face for the whole film. Right? Like, as you can imagine, if you're like watching Avengers and like there's just stuff exploding at you all the time, you know, you're like cross-eyed trying to focus on all of this like smoke in your face, would not be a very pleasant movie-going experience. Might be realistic from like Optimus Prime's perspective, but probably not so great for entertainment. Optimus Prime, he's not an Avenger, right? No?
No, that's a transformer.
Transformer. That's an electrical component. I don't know. Okay, right. And of course, there are many different displays out there. So that's mainly an issue when it comes to like 3D displays that are at a distance. Other kind of stereoscopic displays try and achieve this in this sort of auto-stereoscopic effect. So that would be like just one guy viewing it instead of a whole room of people looking at a far, far away screen. So in that world, you know a lot more, right? Because maybe you know the viewer and the distance that they have to your screen. And so you can actually send out two different signals to the two different eyes, right? You can't do this if you have a theater full of viewers sitting at a bunch of different angles, right? This has to do, by the way, there's a phrase out there called light field, right? So light field rendering used to be really important. The idea of the light field is that like everywhere around us, if you stand at a point and you like point in a direction, you can measure how much light is like at this point going this way, right? And that is like the complete information in the rendering world. And so somehow all these different displays are trying to simulate different light fields, right? And they just, sort of the ones that are the most effective for different applications depend a lot on where you know your viewer is going to be, how comfortable they are, and so on. So in any event, in auto-stereoscopic displays, you know where the viewer is, you know where their eyes are, so you can start to do things like direct out different signals to simulate that light field better, right? There's light going every which way, and they cross over each other in different fashion. And so a very typical display here would be to maybe put a lenticular kind of screen, so you have some very high resolution computer screen, and then you have these little bent lenses in front of it. And what are the lenses doing? Well, the light is coming out of your screen, roughly orthogonally, and these guys are just redirecting it in different angles. And so what this allows you to do is render a slightly different scene going one direction than to the other, which can create the sort of light field effect that you want to see. Right? And so these give you some amount of binocular parallax without having to wear glasses. And the two kind of ways that you do that are either with these lenslets, that's like these little lumpy computer screens you see sometimes. If you want to make a graphics person like really, really uncomfortable, like just scratch your fingers across that lens. Which you shouldn't do because they're expensive and hard to replace. Or you can have a parallax barrier where you just like put your display and then offset from that a little bit, some kind of a barrier so that when the light comes out of the display, it has no option but to go kind of diagonally. So those are the two kinds of technology. So for example, this LG Optimus 3D, this was the 3D phone that was very short-lived because it turned out people didn't really need a 3D phone. I think that one used a lenticular display. The Nintendo 3DS, which to my understanding is much more popular, uses a parallax barrier. Right, and of course, typically these displays are designed for a single viewer at a single distance from the screen, and they look bad at another distance, right? They just don't look good If you want to simulate more of your light field, you can do this. So for instance, maybe you encode a bunch of different views, so like a bunch of different light going in different directions. And then one way to do it would be to have one of these lenticular displays where your lens isn't just like a triangle, but rather a bunch of different facets that send light in different directions. And typically, these are just literally pieces of weird lumpy plastic that you glue on top of your screen, right? There's nothing too magical going on here. But there are many challenges. So for example, if you shift that piece of plastic off a little bit, then suddenly you're creating a totally crazy light field that doesn't make any sense. And of course, once again, as with many of these technologies, well, now what have you done? You've taken your computer screen and you've made different columns of pixels correspond to kind of different directions in the light field, which means that you've just divided the resolution of your screen in a funny way. In fact, moreover, typically these lenticular displays, they're just vertical, right? Because I think there are relatively few 3D displays that'll work well if you like lean down on your knees and like look up at it. Like they're typically just for horizontal motion, which means that the resolution of your screen is different horizontally than it is vertically, which can create some really strange artifacts. So the advantage here is that there's no head tracking, there's no glasses, nothing. But of course, the disadvantages are that there's low resolution, it's very hard to sync up, and it requires some kind of complicated materials that can easily get messed up. But there are all kinds of cool displays out there. I mean, there are ones that have up to like 45 or more views, which is just incredible. This guy seems to be enjoying it. And of course, capture for these kinds of displays isn't terribly complicated either. Like, here's a video from Wojtek, who's professor here in our graphics group. So they had a real-time 3D TV system, and essentially, it's not terribly complicated because the 3D aspect of the display. Whoa. The 3D aspect of the display is just a lens. Like, it's not actively doing computation. And so what you have to come up with is just a clever way to collect that video in a way that is compatible with the lens that you're going to use to display it later. And so even like, what, 10, 20 years ago, they were able to capture this. Let's see if we can. It's kind of fun to look at like what they had to do to capture these kinds of things. So in order to capture something that's compatible with these displays, what do you need to do? You need to have a whole row of cameras that are displaced in kind of a similar fashion. And a whole row of really old computers. So let's see what this looks like at the end of the day. Yeah, and so what you can get is a nice 3D display of graduate students awkwardly tossing balls at very low resolution. Actually, I don't think these are graduate students. This is engineers at Mitsubishi Electric Research Lab, which used to be right around the corner from here. These displays never really caught on. I think that essentially there's sort of a devil's bargain, right? I mean, on the one side you get 3D effects, which is pretty cool. On the other side, the decreased resolution and some of the other visual artifacts that are associated with these displays were really hard to overcome, and just didn't make it worth it, right? I mean, like at the end of the day, this isn't a realistic enough 3D effect for it to be worth all the extra pain. Sorry. Right. In terms of 3D displays, though, there are all kinds of technologies out there. Here's another one where what they did is they took a mirror that you then spin around a bunch of times. This is sort of similar to like what's going on inside of your projector. So now you have a light source, and depending on which way the mirror is pointing, it's like giving you a different slice of the light field that's coming out of the display. The cool thing about these kinds of displays, which are popular, you can usually see a demo of these at SIGGRAPH, is that they're 360 degrees. You can look at it from the top, from the bottom, the side, whatever. They look okay. What's the problem with this kind of display? Yeah.
The bigger you want to make it, the bigger object you have to rotate ridiculously.
Yeah, you have a giant spinning object. You can't put your fingers in this thing, right? And the bigger your display is, the bigger your spinning object is. This is really a problem, right? So like these are fun to play with, and they create that kind of cool sci-fi movie effect. Like you could have like a really weird 3D Skype, and indeed that more or less is possible using this sort of technology. But you'd have to put it in a giant, I mean, you can see here they had to put it in a giant glass box because if you put your fingers in it, it would be quite painful. I mean, think about like your eye refreshes at 30 frames a second, So think about how fast that this thing has got to revolve around so that a viewer at any angle can get that 30 frames a second signal and not feel uncomfortable. So it's amazing they can do it, but still quite difficult. The nice thing about these sorts of displays is that capture typically isn't so hard. When we say capture, we mean like filming, right? Because you just have to film in a fashion that's compatible with the way you display. So it's not like it's computationally expensive, you just need more cameras. And then you can get, I don't know why that's what they chose to film. All right. And then finally, of course, there's volumetric displays. So now maybe you don't want to just see an object, you want to see through it. In medical imaging, this can be important. And there are many different ways to do this sorts of thing. Some of them, these sort of swept volume displays, are quite similar to that rotating mirror. Maybe you have something that's spinning around and giving slices of the 3D object that you want to see. Notice here that there's transparency, which is intentional, which is pretty cool. Or the world's most brain-dead version of a volumetric display literally just has like 4 displays stacked on each other at different depths. And of course, what you see isn't really a 3D object. It's like 4 2D slices, but sometimes that's good enough. And so the early volumetric displays, that's really what they looked like. Although this didn't necessarily make it all that much easier, because now what did you have to do? Well, if you weren't displaying anything in a pixel, it had to be transparent, right? And finding the right kind of material that can do that is a pretty tall order. But finally, of course, these days, the popular displays, and I think where a lot of the engineering is, if you're into this kind of universe, is in the VR and AR world, right? Virtual reality and augmented reality. This is a technology that's changing all the time, and I don't know what the latest thing is because it comes out, I'm sure something else has come out this year. Really, these kinds of displays are cool, and everybody thinks in sci-fi movies that they're the future. Certainly, this dude does, and essentially, this is the way to just remove the physical world from the equation, right? You're just putting a display in front of your entire field of view, or maybe a big piece of it, and blocking out everything else in the virtual reality case. Or in augmented reality, maybe you're taking the 3D world and just adding a little bit on top of it. And of course, these displays are really exciting because they're completely immersive. In fact, it looks like in this particular Oculus demo, they've even clamped this guy's ears into the display just to make sure he's not hearing anything that you don't want to hear.
Those are actually
headphones. Yeah. Well, that is what an ear clamp is. Yeah. Right. But what are the problems associated with VR? You guys know? Yeah.
Two things. One is you can bump into stuff in the real world, and then you're kind of sad. And the other thing is, if you do anything that's slightly not realistic, then your user can get sick very easily.
That's right, and I am a great example of one of these users. So the big issues are typically involve latency, right? Because these displays, there's all kinds of latency problems. I mean, never mind the fact that now you have this highly detailed display run in front of your eye that has to refresh it 30 times a second. When you move your head, what do you expect? You expect your perspective on the 3D scene to change. But of course, you have this fixed screen that's sitting in front of your eye. So in order to do that, it's no longer just a question of display technology. It's also eye tracking and physical motion tracking and all that good stuff playing together. And playing together at such a rate that your brain doesn't notice that it takes some processing time to notice that you've moved your pose and need to render a different scene. Right? And so the big issue in this technology used to be, and oh God, I remember this stuff. It was like being totally, those old drunk glasses that they have in high school? Where like, you turn your head and then like, the 3D screw, display kind of falls behind. That was what the old school VR technology felt like, because the loop just wasn't fast enough. But just recently, the latest sort of technology has reached a frame rate where for a lot of people, not for all, the VR is efficient enough to not make you want to vomit, which is a big feature of the latest technology. And of course, there are many applications out there, everything from simulation to entertainment, engineering is a big one. One of the ones that Google really invested in, and of course has changed a lot over the years. By the way, it's fun to grab images from this sort of movies when you do this stuff, is really in this sort of AR universe, right? So for instance, there was a piece of technology out there by Google, known as the Google Glass, which apparently still exists, but only for sort of commercial application, right? So they pulled the consumer products, which is good because those people were annoying. Where essentially they were saying, well, wouldn't it be great if you could wear your glasses and maybe just in the corner of your eye at all times you can be pinged about your email in case you guys did do that enough to me. And so for a lot of time people thought that was going to be the future. It hasn't quite happened yet, but of course maybe we're almost there. In any event, this kind of technology goes back a long way. People have thought about virtual reality displays since the dawn of putting things in front of our eyes. Indeed, the old, probably the oldest 3D display looks something like what we see on the left-hand side here, which is basically two filters with two different images to display your nice stereoscopic effect, which is not terribly difficult. You just need two cameras or one really coordinated photographer. If you jump forward about 100, 150 years, there's a very famous person in the VR and AR world named of Ivan Sutherland, who made sort of the first eye-mounted display. This thing I think was called the Sword of Damocles. Anybody know where Ivan Sutherland worked, by the way? Piece of history here. At MIT, yeah. It was, I think, in Lincoln Laboratory, technically, but in our neighborhood. This is sort of the first proof of concept. I think a lot of people neglect to realize that really eye-mounted displays date back all the way to the 1960s. This isn't a new idea, but of course Professor Sutherland had to do a lot of things that we don't have to do today, namely like clamp this guy's head into place, right? Right. So there's two different solutions to the head motion problem. One is very careful tracking. The other is glue your head into place. And he went for the latter, which made a lot of sense at the time. And of course, head-mounted displays were popular too. There's a really funny patent from 1916, which is the very first head-mounted display, where you could take that image we saw on the previous screen with two photographs, and now you didn't need to hold it in front of your face. I really love that it had a little spike on the top. I don't know why that was necessary, but indeed, if you look at the old patent, the spike is a necessary piece of the head-mounted. It's probably what's missing from the Oculus today. Nintendo, back in 1995, announced one of the very first head-mounted displays with the Game Boy. This was a technology that did not live. I remember when it came out, and we were all very excited for about 10 minutes, but of course there wasn't any kind of eye motion tracking at all. It was basically just a Game Boy mounted to your face. And then now the tracking technology has gotten a lot faster, processing is more efficient, and so on. There's this big explosion in different technologies that's changing all the time. And now there's just this giant zoo of displays here. So if you think about, like, well, what enabled us to make this transition from our original 3D display to what we have now, of course there are many. So in the 1960s, there was this sort of electronic digital revolution, which is what led Sutherland to make his first, I don't know if you call it a display mounted on a head as much as like a head mounted on a display. Then, of course, in the 1980s and 90s, there was a lot of excitement about human-computer interaction, haptics interaction, and so on. And then finally, in the 2000s, co-evolving with your cell phone, was this idea of decreasing the cost and increasing the resolution, decreasing the latency of the displays that we have now. But if you look, I mean, already a lot of the pieces were there a long time ago. So here's, in a little more detail, Sutherland's display from 1968. And you can see that there were two CRTs. There was a little bit of rendering going on, some early, I'm sure, two-dimensional rendering algorithm. I think there was a little bit of head tracking, so it's not entirely true that like it just mounted your head in place. I think there was like a mechanical device there that could keep track of a little bit of your motion, which of course, I suppose you might call interaction in some universe. And really, you know, like the modern Oculus display, this one isn't even modern anymore, are not all that much different, right? I mean, there's just two displays, you got two eyes, there's some amount of head tracking and so on. There's something that was really ahead of its time. But of course, I mean, if you think about it in the history of graphics we've talked about in this class, at the time he wasn't working with a GPU, he didn't have rendering algorithms, nothing. So he had pretty limited ingredients for the display that he had. I'm actually unclear. I don't know if physically that display exists somewhere, like at the MIT Museum or something. I meant to look into that. In any event, there's a lot of considerations that go into designing these things. The main one is the field of view, which is exactly what it sounds like. Right? So you have, your oculus is mounted onto your face. You have two options for what's in front of your eye, right? It's either pixels or it's nothingness. And of course, the more space that you take up, oftentimes, although not always, the better. And so when you look at statistics related to these kinds of displays, they'll often give you kind of an angle, which is like the angle out from your eye worth of display that you see. And there are many trade-offs here, right? So for instance, you can get a wide field of view quite easily by placing a lens there and having the same display, but of course, your resolution, in effect, decreases because you just spread out your pixels more. And there are many clones of this stuff. As sort of an alternative to that style of technology was the Google Glass, which, try as they might, Google really didn't manage to sell very successfully. So this, rather than being VR, was augmented reality. I'm unclear. In any event, the idea here was that you would just look out into the real world and put your email on top of it. And so in order to do that, they used sort of a beam splitting style setup, right? So this is a very different kind of technology where the field of view, in this case, would be extremely small, right? Like you don't want to beam light all the way in front of your face while you're trying to like actually look at stuff. That wouldn't be so great. And so what this kind of technology makes use of rather than a display is an old school illusion. It's kind of cool in VR that most of the techniques out there, we've been around since the 1800s. These are not new ideas. What's new is just the latency. This makes use of the Pepper's Ghost illusion. Has anybody ever heard of this before? It shows up in theater classes sometimes. So like, let's say that I have a theater production and there's a ghost involved. This is a problem because we don't tend to have those as actors. And maybe we want the ghost to appear in the middle of a scene. What can we do? What is a person to do? Well, one thing we can do is we can have our scene, and maybe the viewers are off to the side, and we have something like a piece of glass. And glass has this property that typically, when you have a dark scene, this really is used for ghosts, because in ghosts you tend to be in a dark room, which is where this effect works well. What happens when you look at a piece of glass and it's dark? You see through it, yeah? But now, let's say that I'm standing in front of a piece of glass and I shine a big flashlight, not on the piece of glass, but on my face. What do I see? You see a reflection, right? And so the Pepper's Ghost illusion, what they would do, they wanted a ghost to suddenly appear on the stage, so they put a big piece of glass in front of the background of the scene in the theater production. The ghost would be standing off to the sides of the stage, so they wouldn't be on the stage. And then suddenly when the ghost appears, they turn a big light on the ghost, that reflects off the glass into the audience, and what you see is sort of a funny 3D effect. And so here's an example. I found this funny YouTube video of a guy doing it with his Legos, which I was kind of entertained by. Let's see here. He did a remarkably good job. Yeah, so here's a scene, like some object, and as you shine light on it, you can see it kind of looks like 3D effect. So what you're not seeing here is like a piece of glass. Yeah, there you go. So there's the basic setup. This is some like maker guy's webpage, so they want you to like do it at home. Let me see if we can. Yeah, so like here's an example with like a mask and a window, and you can creep out all of your neighbors on Halloween. Man, he just like really wants to give you instructions on how he did it. I just want to see it. All right, I give up, but you get the idea. Maybe. All right. Well, it's not that exciting. Yes?
I think they did something, maybe they used Pepper's Ghost to make like Tupac appear on some MTV.
They did, yeah. They took him back from the dead. And that was a big, in my generation, that was a big event.
And now
people
are like, hey, is it okay to do this and make hologram celebrities?
Yeah, the main thing, I remember when they did this, yeah, they brought Tupac back from the dead, which was just really troubling for any number of reasons. And the main ethical problem was whether you could call it a hologram, because it wasn't, you know, which really stressed me out, but that didn't seem to be what people were really hung up on. I will let you make your own decision about whether that's okay or not, but indeed, yeah, this was the same illusion used there. So in Google Glass, this is essentially used because they have a piece of reflective material, and what they're shining onto it is your email in very bright color, and that's what gets reflected to your eye, and other than that, you just see through the display. Yes?
The peppers ghost thing,
Uh-huh.
the examples that we saw, it was kind of like you're shining light on like a stationary object,
Yep.
and then you see the reflection. Is there any way to make it so that you would have, I don't know, like a video playing or something?
Oh, absolutely, yeah. I mean, the only reason...
Show up in like kind of
Yeah, so this isn't a stationary object. This is a dude in a sheet. Yeah, essentially what you need is just some source of bright light to come off of the object that's getting reflected into the scene. Yeah, so like the Google Glass is a good example of that. It's actually a display, right? It's producing your email and then reflecting it off of there. Yeah. When it comes to AR, one of the big realizations people had, in augmented reality, it used to be the case that people worked very hard to have a transparent, like a piece of glass, and then to superpose signal on top of that. What people realize in AR is that like your camera, your cell phone has a really good camera in it, and it's so good and so fast, you can take in an image of the scene, edit it in some way, and then display it so that your camera isn't really see-through, but it kind of is, right? Because it's taking in the image and then just displaying back the image as if you were seeing right through your camera. And the advantage there is that you can process the whole image digitally rather than like coming up with some fancy display that's like trying to draw stuff on top of an otherwise clear piece of material, which just from a materials kind of optical perspective is difficult. And so the main AR technology these days probably would be disappointing to us 20 years ago, is literally blocking the world in front of you and then just displaying exactly what's on the other side. And of course, what's really assisted that technology is the fact that, you know, your latest generation of cell phones often has 2 or even 3 cameras in it, and so it can sense depth, and that's what's allowing you to do things like, you know, hold up your camera, put a, you know, view the scene behind your camera, place a sofa on the 3D scene, and go look around, which I think the Wayfair website allows you to do. I was just playing with recently. So anyway, this is just a giant universe. In the slides, I've included a little bit of information on like a whole different tree of different considerations people have when they talk about head-mounted displays. Like, do you have see-through videos, optical stuff? Is it just opaque, but then you're like have a camera on the other side that's displaying, you know, taking the world and then displaying it again? Do you care about the colors, luminance, contrast, and so on? And so there are all these different plots that people use to understand the differences between these technologies. And I think at this point, it's still not clear who's going to win or what's the best one. But I think it's going to be really exciting. This is like one of these universes where, you know, hold on a couple of years and you're going to see some really cool stuff. The question that is less clear to me is whether anybody's going to care. And that's where this universe has really had some trouble. That like, VR equipment's really cool, and the gaming industry's been really excited about it. All these other cool, you know, Tom Cruise style sci-fi movie applications that we thought were going to be really important, like creative ways of interacting with your computer and so on, just haven't caught on. And so I think we really haven't found the killer app for this stuff outside of gaming and entertainment. But we'll see. But anyway, we're a little low on time, so maybe we'll call it for the day. So again, as a reminder, on Thursday of this week, we're going to have lots of special presentations with graduate students that put their heart and soul into sharing their exciting research with all of you. So I encourage you to join us. And then in the lecture after that, it's going to be on you guys. Okay, so we're going to send out a calendar soon with signups for presentation times. Please do that. You can't do this one late, sorry. And yeah, we'll see you then.